Swayam Prabha. Digital India. Educated India.
Good morning. From this lecture, we start the third module of our course, which is on numerical analysis, numerical methods. So, in this lecture, we will concentrate on solution of equations and their systems, and next lecture onwards, we will start our study of numerical optimization techniques. So, first we start with polynomial equations. The fundamental theorem of algebra tells us that a polynomial of nth degree has exactly n roots, and with those roots x1, x2 up to xn, you can factorize this polynomial in this manner. Now, in general, the roots are going to be complex. Now, as a special case, it may happen that you get real roots. However, with real coefficients, if complex roots appear, then they always appear in conjugate pairs. So, this is one important piece of information which helps us in many of the methods to solve such polynomial equations. So, this is a polynomial. This polynomial equated to 0 gives us the corresponding polynomial equation. So, we can talk of the roots of the polynomial or the solutions of the corresponding equation. Now, in the equation solving process for polynomial equations, there is a lot of theory which helps us or which guides us in several different manners. One of them is Descartes' rule of signs, and then the other is bracketing and separation of different roots, and then there is a process of synthetic division, in which if we have a polynomial px and we have another polynomial qx of lower degree, then with qx we can divide the polynomial px, and the quotient is fx and the remainder is rx. Now, f and q, they are interchangeable. If you take fx as the divisor, then qx will be the quotient and rx is the remainder. So, the remainder is a polynomial of a degree lower than the divisor by which you try to divide the original polynomial. It is exactly like ordinary arithmetic division. Now, one more important point is the multiplicity of a root. All the roots need not be different. There can be some roots which are repeated, still they are counted in this n roots. Okay. So, for a cubic polynomial, the roots could be 2, 3 and 3. So, they are counted as 3 roots if 3 appears twice in this factorization. Now, the simplest polynomial equation that you can think of is of course linear equation, which is extremely simple. So, from the next step onwards, the thing becomes slowly more and more difficult. Above linear equation, you have got quadratic equation, which all of us studied in school. So, this quadratic equation has this solution, that is, there are two solutions with plus minus signs. Now, depending upon what is b square minus 4ac, the solutions could be complex or could be real. Now, the way this formula is arrived at is of course through completing the squares, and from which, taking the square root from here, we get this expression. Now, the same thing if we try to do in the case of cubic equation, then we would be thinking of completing the cube, right, so that you can take a cube root and get the values of x. Now, this is comparatively much more difficult compared to quadratic equation, and that is why it took a long time for mathematicians to arrive at a good way to solve this problem analytically. Cardano's solution proceeds like this, that is, for completing the cube, in some sense the process succeeds if this x square term is missing from the equation. Now, how to make it missing, how to get rid of this x square term. So, the way he handles this problem is by substituting y equal to x plus k here, which will transform this equation to y in this manner. Then we say that let us choose that k which makes this y square term vanish, and that k is a by 3. So, by choosing a by 3 as k, we get this term as 0, and then y cube plus something into y plus something equal to 0. That becomes the transformed equation in y. So, in this manner. Now, solution of this is possible in a process which is something like completing the cube. So, for that y is assumed in this manner, u plus v, and if you take the cube of this y cube, then you get this expression in which there is another u plus v appearing here. So, if we write this u plus v as y, then you note that this equation and this equation can be compared, y cube, py, and as you bring this on this side, you get minus 3 u v y. So, p becomes equal to minus 3 u v, that means u v is this, and then q here and negative of this term for this equation. So, u cube plus v cube become minus q. So, in u and v you have got two equations. Okay. It is not very difficult to solve this, because here you have got u cube plus v cube, and with the help of these two equations you can develop another equation in for u cube minus v cube. So, that is a plus b whole square minus 4 ab is a minus b whole square. When you use that formula, you get this. The square root of this second one gives you u cube minus v cube is equal to plus minus the square root of this. So, there are two equations. The first one gives you the sum of u cube and v cube, and the second equation will give you the difference of the same two things. So, half the sum gives you u cube and half the difference gives you v cube. So, you solve u cube and v cube from these two and get this. Let us call these two as a and b, plus minus you get. So, you get two values a and b. So, one of them you can call u cube and the other you can call as v cube. After that, you take the cube roots of a and b, and while taking cube roots, keep in mind that if this thing becomes complex, then you have to appropriately take its angle, and in the cube root the angle will get 1 by 3, 1 by 3, 2 by 3 and full. So, like that. So, that means in the cube root, so if the description of that number in the complex plane turns out to be like this, then its cube root will have 1/3 of this angle plus 120 degree and then plus 120 degree, whatever that was. Okay. So, these will be the arguments of the three cube roots. Okay. So, even if this is real, the three cube roots will be one which will be real, the other will be at 120 degree and the third will be along 240 degree. Okay. So, that way we take the three cube roots of a and b. So, you can show it as if one of the cube roots is a1, the other one will be a1 omega, the third one will be a1 omega square. Similarly, on this side. Okay. Now, with this, with u chosen from here and v chosen from here, you can combine u plus v in 9 different ways, but all of them will not satisfy this equation. Only 3 of them will satisfy. You can verify this fact. So, if it happens that a1 and b1 taken from these two and added together becomes one root of this equation, satisfies this equation, then the other two will be a1 omega plus b1 omega square and y3 will be a1 omega square plus b1 omega. This is the way it is. And you will also note that out of these 3 roots, one of them must be real, because this is a cubic equation. So, the solutions of it, the roots of a cubic polynomial, if they are complex, must appear in complex conjugate pairs. So, that will be able to account for at most an even number of roots. So, only 2 of them can be complex, the third one, the odd member out, will be essentially real. So, this is one situation that you will always find when the degree of the polynomial is odd. Now, after this cubic equation was solved by Cardano, then mathematicians tried for quite some time to solve the next higher degree equation, that is the quartic equation, 4th degree equation. And Cardano's own student Ferrari found a method again based on completing the squares to solve for the 4th degree equation. So, suppose this is a 4th degree equation given. Of course, the leading coefficient can be taken as 1, because whatever else appears there, you can divide the entire equation by that number and put it in this manner. Now, if you keep on this side, on the left side, only the 4th degree and 3rd degree terms and complete that as a complete square, okay, compensating by the term a square x square by 4 on this side, and take all these other terms there, then you get this expression. On this side you get a complete square. It would be nice if at the same time you got a complete square here also. Then both sides you could take square root and reduce the degree of the equation. But then that cannot be always possible, because this expression is dependent on the a, b, c, d coefficients given in the original problem, that is not in our hand. So, in general this will not be a perfect square of a linear expression. So, we need to make it a square by doing what? By adding certain things here and adding compensatory terms on this side also. So, inside this complete square we add a term from our side, we add a term y by 2, and the corresponding compensations, there will be 3 compensations: y into x square, which is here, and then y into a by 2 x, which is here, and y square by 4, which is here. Okay. So, by adding these compensatory terms, we extend this perfect square on this side and then ask the question, what is the value of y for which this side also will be a complete square of a linear expression of x. Okay. Here we could not say that, because we had no freedom. Now, we have introduced y, so we can ask for y to satisfy some requirement that we supply. So, we ask under what condition this will be a perfect square, and that condition we know. That condition is that square of this coefficient is equal to 4 times the product of these 2 terms, parenthetic terms. When you impose that condition like this, b square minus 4ac equal to 0, then and simplify this, then we get a cubic equation in y. That means any solution of this cubic equation taken as y, if we insert in this equation, then the right side will be a complete square. So, now the question is how to solve this cubic equation. We have already seen how to solve a cubic equation. So, by that method, Cardano's method, or by any other method, if we can solve this cubic equation and take any one of the 3 roots, any one of the 3 solutions for y, and typically we will take the real solution, because cubic will always have a real solution. So, typically we will pick up a real solution from this cubic equation, dump it here, and then you will find that this right side becomes a perfect square. So, these are the steps. First, frame the cubic resolvent. This is called the cubic resolvent of a quartic. Okay. So, in that a, b, c, d we know from the original problem. So, we insert those things and frame this equation. So, that is the cubic resolvent of a quartic equation. Solve this cubic equation, pick up one solution as y, insert this y into that equation to get the right side in the form of a perfect square. The moment we have come to this point, we immediately take square root on both sides. So, this stuff turns out to be plus minus ex plus f, right, and if we take the plus sign, we get one quadratic equation. If we take the minus sign, we get another quadratic equation, and these 2 quadratic equations we can separately solve. We get 2 roots from here and 2 roots from there, and that completes the solution of the 4th degree equation. Now, after the 4th degree equation, general quartic was also solved in this analytical manner. Then people started thinking in the next stage, that how about higher degree equations. Till it was proved by the Galois group theory that a general quintic or higher degree equation is not solvable in this analytical style. Only iterative numerical methods one can use for solving general equations of degree higher than 4. And that means we have to rely on iterative processes, but then iterative processes are of two kinds. One kind of iterative processes for equation solving are general. They are for general nonlinear equations, which will apply to polynomial equations also. But then there are some methods which are specific to polynomial equations, and they operate with much higher efficiency on polynomial equations. So when you need to solve a polynomial equation, then try to use one of those methods which are specific for polynomial equations. On the other hand, for general nonlinear equations, you have no option. You have to apply the general iterative numerical processes. So the specific methods for polynomial equations are somewhat analytical. They have an analytical base, and partly they are numerical, partly iterative. So one method is through the companion matrix. In one of the exercises in one linear algebra chapter in the textbook, you might have found a problem in which it was asked to find the characteristic polynomial of this matrix. If you try to find the characteristic polynomial of this matrix by the standard process, by lambda I minus this matrix determinant u equal to 0, and then expand that determinant, then you get the characteristic polynomial exactly like this, the typical form in which you would supply a polynomial equation, okay, polynomial. So then you find that if the characteristic polynomial of this matrix turns out to be the polynomial that we have in hand, then to find the roots of the polynomial, we can try to frame this matrix and call it the companion matrix, and then solve an eigenvalue problem for this matrix. So you find that if the matrix is very small, say up to size 4, then the correct way or simplest way to solve the eigenvalue problem is to frame the characteristic polynomial and find its roots. On the other hand, if the eigenvalue problem is of a much larger size, the matrix is very large, then that is found not to be a good method. For that purpose, we studied a lot of other eigenvalue problem methods. Now if we find a polynomial of large degree and we want its roots, then one way is to frame the companion matrix and then find its eigenvalues. Okay. So this is one of the best methods for finding the solutions of large degree, high degree polynomial equations. There is another method which is Bairstow's method, which also works very nicely on polynomial equations. What it does is that from a given polynomial, it tries to separate out factors of small degree. Now if you try to attempt separating real linear factors like ax plus b, then that may not succeed always, because a priori you do not know whether the equation has real solutions, whether the polynomial has real roots. But then you know that if it has complex roots, then complex roots always will appear in conjugate pairs, and when you multiply two such factors in which alpha and alpha bar are conjugate pairs, then the product gives you a polynomial which will be in the form x square plus something x, this is real, plus something, this is also real. So sum of the conjugate pairs is real, product is also real. Okay. So like that you will find. So this quadratic factor will certainly have real coefficients if the original polynomial has real coefficients. So we do not attempt to separate out real factors, real linear factors, but real quadratic factors. So for separating out a real quadratic factor, what we do? We propose a factor like this, x square plus q1 x plus q2, and conduct a synthetic division, okay, of the given polynomial. So, after completing the synthetic division, there can be a remainder. If this is actually not a factor, then there will be a remainder. If this is a factor, if our guess is perfect, then this is a factor, and in that case remainder will be 0, and it will confirm that this is indeed a factor. On the other hand, at the starting point, in general, we would not be able to make a correct guess, so there will be a remainder. Remainder will be a linear remainder of degree less than this, right? So, the linear remainder will be like this. Now, let us examine these two numbers r1 and r2 that will appear in this linear remainder are as a result of these two choices q1 and q2. So, if we choose different q1 q2 values, then we will get different r1 r2 values. So, that way we can say that r, this vector r1 r2 is actually a function of this vector q1 q2. That means, this r is a vector function of this vector variable q. This also has two members, this also has two members. So, then we say that now we try to write that as if this is a function. So, r of q equal to 0, this system of two equations in two unknowns, the unknowns are q1 q2 and equations are these r1 equal to 0, r2 equal to 0. So, these two equations in these two unknowns we try to solve. That means, iteratively we change q1 q2 values in our guess, which will make the remainder vanish. Okay. Now, this is actually analogous to the typical process of Newton-Raphson method, which is Jacobian based, and in the case of polynomial equations, there is a specific way to develop the Jacobian and apply iterations, which is much more efficient compared to a general case. So, in the exercises of this chapter, there is one problem, one exercise in which the step by step process has been given to establish this particular method and then use it. I strongly advise you to carry out the operations once, to be at home with the method how it operates. Next, we continue into the case of two simultaneous equations. For that matter, one purpose of including the equation solving process in this course is basically to include methods for systems of equations. Okay. So, if we have two simultaneous equations in two unknowns, now polynomial based methods operate in a particular way in which we try to eliminate one of the unknowns and get a single equation in the other unknown. So, if there are two polynomial equations in x and y like this, then rearranging we can express these two equations as if they are equations in x only. In the coefficients, you will get terms containing y. A1 and A2 are simply P1 and P2 as appearing from here, and B1 and B2 are linear expressions of y, including this and this term, and C1 and C2 are quadratic expressions of y, including this term and this term, right. Whatever they are, for the time being we club them together. Then we approach our school knowledge of common root for these two polynomials, common solution for these two quadratic equations, and the result is given by Cramer's rule. X square by b1 c2 minus b2 c1 is equal to minus x by a1 c2 minus a2 c1 is equal to 1 by a1 b2 minus a2 b1. So, that we write. Now, if we consider these two, the equality of these two, then from there we get one expression of x, that is x square by x, that gives us one expression for x, that is minus this thing divided by this thing, that is this. On the other hand, if we use the equality of these two terms, then we get x by 1, which is minus this by this, so that is this. Now, the condition for common solution of these two quadratic equations for x is that these two must indeed be equal, okay, and that means that product of these two, cross multiply these two. So, product of these two is the same as product of these two. That means, this into this is equal to this whole square. So, this is the condition for common solution of these two quadratic equations. Now, for x, that is the condition, but for y, what is it? As you equate this to 0 and insert b1, b2, c1, c2 as expressions of y from which they were earlier found, then this will turn out to be a 4th degree equation in y. Okay. So, if you use that 4th degree equation to, if you solve that 4th degree equation for y, then in general you get 4 different solutions. Each of those solutions, as you insert here, you get one solution for x. Okay. So, that way for x and y combined you get 4 solutions, which will be the case because these are both quadratic equations and the maximum number of solutions that they can have together is 4 only. In general, you can say that two equations in x and y of degree n1 and n2, out of that if you can eliminate x, the x eliminant turns out to be an equation of degree n1 into n2 in y. Okay. This number is called the Bezout's number. There are several methods for elimination of unknowns from simultaneous polynomial equations. Two of those methods are quite effective. One is called Sylvester's dialectic method and the other is Bezout's method. We do not go into that in detail because those who are interested in this polynomial system of equations, they can look up particular texts and courses for theory of equations itself. Now, after this we will continue into the discussion of those methods which are general, which will solve polynomial equations as well as transcendental equations. They are purely numerical methods. A typical general nonlinear equation can be expressed in this manner, f of x equal to 0, and the practical problem. Now, in the case of general nonlinear equations, transcendental equations, we do not ask how many solutions this will have. Typically, we do not ask, because quite often enumerating the solutions, that is working out the number of solutions that equation has, is quite cumbersome. So, the practical problem is to find one real root of f x or one real solution of this problem. So, this entire study is typically conducted for real solutions, unlike the case of polynomial equations, in which case we are quite often interested in the complex solutions as well. In the case of general nonlinear equations, we typically look for real solutions only. So, examples of f x, it can be a polynomial or it can be something like this and so on. So, for this kind of problems, for solving general nonlinear equations, a few background processes will help us in tackling the correct interval in which we would expect a solution. So, for that we use the method of bracketing. If we can identify 2 points, say x0 and x1, in which the function value f of x is of different signs, then if the function is continuous, then we can use its continuity to claim that between x0 and x1 there must be a point where the function crosses 0, and that point gives us a root. So, now after bracketing the root in that manner, all that remains is to hunt out the root in that interval. One straightforward method could be bisection, that is, given the interval x0 x1 which gives a bracket, we look for the sign in x0 plus x1 by 2. Now, depending upon what is its sign, this midpoint will replace either x0 or x1 and then continue. So, bisection itself is one viable iterative method for solving an equation like this, but it is costly. There are much more effective methods for solving the problem, but you can always consider bisection method as a fallback if in some iteration the other sophisticated methods somehow get into some trouble. So, bisection method remains one method on which you can always rely, as long as you have a bracket to start with. So, what are the other sophisticated methods? One is the fixed point iteration method. So, what we can do is that we can rearrange the given equation in a manner such that x is expressed as an expression of x itself. Now, for example, take this example of f x. So, the solution of the equation tan x minus x cube minus 2 equal to 0 is required. So, f x is this. Now, if this equal to 0, then we can arrange that equation in the form of an expression for x in terms of x itself, call that expression as g x. There are several ways of doing it. One possibility is to take these two on the other side of the equation, x cube plus 2, and then say then x is tan inverse that. The other possibility is take x cube only on the other side, and then on this side you have tan x minus 2, and then cube root of that will be x, or dividing tan x minus 2 by x square, you get another expression for x. So, all three of these are candidates for suitable g x that you can frame out of this equation and try to iterate. Now, what is the iteration? Iteration is very simple. The iteration has two steps. Starting from a guess value, all these iterative processes will start from one guess value, you see. So, starting from a guess value x 0, evaluate this function, and since we are trying to solve x equal to g x, then whatever is the value of this function, that becomes the next value of x, x1. So, then that x1 goes here, whatever comes out, that becomes the next iterate for x, that is x2, and so on. So, this continues hoping for convergence. Now, as I say, hoping for convergence. For an arbitrary arrangement like this, there is no guarantee that the process will converge. If the solution is say at 5.2, then if you make a wrong kind of reorganization, then it may happen that even starting from 6, it might go to 10 and then 16 and then 79, and it may diverge. So, convergence as it is not guaranteed. Then we ask, what is the question, what is the condition under which the convergence is guaranteed? There is a condition. So, to discover the condition, see the way this process will work. Suppose after organizing x equal to g x, we have got this curve as the graph of g x, and so y equal to g x is this graph, okay, this curve, and y equal to x is this 45-degree straight line. Now, y equal to g x and y equal to x intersect at a point where x equal to g x is satisfied. Those are the points which we are looking for. As shown in the figure, there are two such points. One is x star and the other is x bar, at which this curve and this straight line intersect. Now, suppose we start from this value x equal to p. As we were just discussing, the iteration is just two steps. At the current point, evaluate the function g of x, and then whatever is the value, assign it to x, and this process is continued. So, at this point x equal to p, evaluate the function. That way we get this value, which is a. So, then from there, this value now has to be assigned to x. That means parallel to the x axis, that is horizontally, if we move and then meet the y equal to x line, that means this y value will be here same as the corresponding x value. So, at this x value, then we evaluate the function g x, arrive at the point on the curve, and then again horizontal vertical, we do converge. On the other hand, if you start at q extremely close to the other solution x bar, you would expect that quickly it would converge to x bar, but that does not happen. See, from q we evaluate the function, reach this point L. That value of g x, that is y, we assign to x, that means we come here. At that value we evaluate g x again, we come here. Look, we are not going from q towards x bar, but we are going away. If we start on the other side of x bar, say at r, again evaluate it here, come here, go there, u, v, w, we are again diverging on the other side. So, what is wrong here? So close to x bar, we are not converging to x bar, whether you start from this side or that side. On the other hand, so far away from x star, we could happily converge. So, what is the difference? So, if you analyze the situation, you will find that if there is an interval bracketed situation in which there is a unique solution x star, then and apart from that, if the reorganization has been done in such a manner that g prime has an absolute value which is less than 1 in that interval, then any point started with in that interval will converge to x star. Okay. That means the slope of this curve in the interval, if the slope of that is not greater than this slope of this line, then the process will converge with guarantee, otherwise not. The next method for solving a nonlinear equation is the Newton-Raphson method. This has a connection with the Newton's method of optimization theory as well. So, this method relies on the first order Taylor series of the function f x, which is like this. This is the first order truncated Taylor series. Now, the understanding is that we have got a value of x where we have evaluated the function and its derivative, and we want to move to a new point x plus delta x where the function value is 0. So, if we want f of x plus delta x to be 0, then for that purpose we equate this right hand side to 0, and from there we get a value for delta x, which is minus f x by f prime x. Now, when we add this delta x value to the original current x xk, then we get this expression for xk plus 1. This is the typical update formula. If you examine this formula carefully, you will find that this is one way of writing x equal to gx. On the left side you have the next value of x, on the right side you have an expression of the current value of x. Now, for that gx, if you work out the same convergence requirement as the fixed point iteration formula, then you get the convergence criterion to be this. If this is satisfied in an interval, then the starting point from within that interval will converge to the root in that interval. The geometric interpretation of the working of Newton-Raphson method based on this formula is the following. You start from a guess point and evaluate the function and reach this point. At this point, make a first order approximation of the curve, that is a tangent approximation, tangent based approximation. So, that means draw a tangent to the curve at this point, and wherever that tangent crosses the x axis, take that as the next point. Again, from there evaluate the function, reach the point on the curve, draw the next tangent, and so on. So, started from x0, you will travel as a, b, c, d, e, f, and like this you can converge to the value x star, which is the root of this particular function f x. Now, the merit of this method is that it has a quadratic speed of convergence, that is, at every iteration the accuracy gets improved by somehow 2 orders. Okay, the accuracy gets improved by 2 orders at every step. So, this is called the quadratic speed of convergence. The demerit is that if the starting point is not appropriate, then there is no guarantee that the process will converge. So, sometimes Newton's method is found to wander haphazardly and go away from the solution. It might diverge, or sometimes it might oscillate from here to on this side, then on that side, again on this side, and sometimes the Newton-Raphson method is found to oscillate around the solution also rather than converging. So, these are some of the demerits that Newton-Raphson method has, but when it works, if started close enough and if the function derivative is good, the rate is good, the slope is good, then when it converges extremely fast. Now, in this particular iteration formula, if we replace the derivative by a finite difference kind of first order derivative, then what you get is the method of the second method. So, rather than tangent based method, you get a secant based method, that is through a chord cut through 2 points on the curve. So, replacing f prime by this expression, you get this iterative formula, that is called the secant method. So, the way it works is that start from 2 points x0 and x1. At these 2 points, evaluate the derivative, evaluate the function values. No need of derivative here because derivative is replaced by this. Then through these 2 points, draw a chord of the curve. Wherever this chord cuts the x-axis, take that as the next point. Then out of x0, x1 and x2, retain 2 points and continue the process. Now, this is the second method, and a particular case of second method in which the initial 2 points are taken in such a manner that the function value is positive on one side, negative on the other, and at every step that bracket is maintained. That method is called, that method is a special case of second method, and that is called regula falsi or method of false position. In this particular case, since we are maintaining a bracket always, so convergence is guaranteed. This is a very reliable method. Now, there are other methods also to solve nonlinear equations. One of them is quadratic interpolation or Müller's method. In that, what you do is that you do not talk of derivatives at all for evaluation. You take 3 points at which the function is evaluated, and through 3 points you can develop a quadratic model for the function, a local quadratic model, and then say we want to find out at which value of x this is 0, and that point is the next point that we have. So, that means started from 3 points, this model gives a quadratic approximation for the function in the local neighborhood. So, we equate that to 0 and solve for x, and then with the old 3 points we have got a fourth point. Out of these 4 points, depending upon the function values, we retain 3 and throw away the worst point and continue this process. Okay. So, this is quadratic interpolation. Of course, in this we have to solve a quadratic. Solution of a quadratic is not difficult, but then questions that arise is that what if that quadratic has 2 solutions, which one to take? Then if both the solutions are complex, then we have nothing in hand. In comparison to that, there is another method which is called inverse quadratic interpolation, which is found to be much more straightforward. From the same 3 points that you start with, do not frame y as a quadratic expression of x, but x as a quadratic expression of y, and then for y equal to 0 you get x equal to a. Take that value of x as the fourth point, and again out of the 4 points available, drop 1, retain the 3 best and continue. This is called inverse quadratic interpolation. Combining this, combining this with many other aspects, you have got a very good professional method for nonlinear equation solving, that is called von Weingarten-Decker-Brent method, or in brief Brent method. So, see here, through the same 3 points x0, x1, y1, x2, y2, the quadratic interpolation will give you this curve, from which you might take this point or this point as the next point. The inverse quadratic interpolation, on the other hand, would give you y. Okay, quadratic interpolation gives you this curve, y as a quadratic expression of x, and inverse quadratic interpolation will give you this parabola. Both are parabolas. So, the same 3 points. Okay, same 3 points. This is the parabola that you would get in the case of quadratic interpolation. This is the parabola that you would get in the case of inverse quadratic interpolation, which will cut the x axis only at one point. Okay. Now, in the Brent's method, there are quite a few aspects that are combined. First of all, it starts with a bracket. Out of the 3 points that we have in hand, the 3 points must fall on 2 sides of the solution. That is, at least in one of the points, the sign of the function must be opposite to what is the sign in the other 2 points. So, and that bracket is always maintained. So, you never drop the solitary point on the other side, retaining all 3 points on one side of the root. You never do that in Brent method. You always maintain the bracket. Second, you use inverse quadratic interpolation, that is this model. And whenever you find that the next suggestion of a point that you get out of this turns out to be within the bracket interval, you accept it. On the other hand, if you find that the suggestion x equal to a turns out to be outside the current bracket, that means rather than squeezing the bracket, it would enhance the bracket, which is not desirable. then you say that for that particular iteration we do not accept the suggestion of the inverse quadratic interpolation, rather for that particular iteration we replace that step by a straightforward bisection step. So, whenever we find that the sophisticated method suggests something good, we accept it, and if it suggests something undesirable, then we do not accept it, and for that particular iteration we use our time tested, reliable and guaranteed method of bisection for only that step. So, when the bad time comes, we look for a slow but assured step, and when good times proceed, we approach the solution faster. So, this is a kind of opportunistic maneuvering between a fast method and a safe method. This kind of situations we will come across quite often when we go into the optimization methods. In this context, it can be noted that many of the equation solving processes are deeply related to many of the corresponding optimization processes. They have the same background of the iterative schemes. Now, we proceed to the system of nonlinear equations. If you have got a number of equations in a number of unknowns, then concisely this system can be written like this, where f is a vector function of a vector variable x. Now, in general, it could be that the dimension of x is greater than the dimension of f, or the other way around. If the dimension of x is greater, that means you are trying to solve less number of equations in more number of unknowns. That is an underdetermined problem, and you would expect infinite solutions if there are solutions at all. If the system is consistent, then you would expect infinite solutions. On the other hand, if the number of x's is less, then in general you would expect conflict, and then you talk of least square problems. That is, to the extent possible, you can try to satisfy all the equations if the number of equations is larger. The most often encountered situation is when you have n equations in n unknowns. So, that means in which case you will expect a finite number of solutions, not necessarily unique, but a finite number of solutions. That is what you would expect, but you might find one of the other cases also in that case, but typical expectation is a finite number of solutions in that situation. So, now one comfort of a single equation is lost. You cannot talk of bracketing at all, because it is not a one dimensional line anymore, it is a multidimensional space in which you have to make the search. And if you try to work out fixed point iteration schemes like this, then there will be so much of possible reorganizations of these equations that you cannot enumerate them out. So, you try to establish those kinds of reorganization schemes which come from some straightforward theory, rather than haphazardly trying the recombinations. The most obvious candidate for that purpose is again Newton's method or Newton-Raphson method, which we get from the first order truncated Taylor series of this vector function of a vector variable, and that is f of x plus delta x is equal to f of x plus the Jacobian multiplied with delta x. The higher second order terms for the time being we neglect. Now, if f of x plus delta x is roughly equal to this, and if we have a starting value, starting vector x, say x 0, and we want at the next point this function value to be all 0, then we equate this to 0, 0 vector, and then take f x on the other side, pre-multiply with the inverse of j x, and that gives us delta x. That delta x we add to the current x and get the next x, right. So, the next value of the vector x is current one minus j inverse f. So, this is a typical iteration of Newton-Raphson method for solving a system of nonlinear equations. This matches exactly with what we had earlier for single equation. For a single equation, we had this. Now, again f of x k is here, f of x k, and division by the first derivative is now replaced with pre-multiplication with the Jacobian inverse. Okay. Division by a matrix you cannot conduct. So, the corresponding operation here is pre-multiplication with inverse. So, for that matter you could write it as minus 1 by f prime into this, that is f prime to the power minus 1 into this. So, that J inverse is here, okay, Jacobian, that is the first derivative. Now, this method of solving a system of linear equation, nonlinear equations has its usual merits and demerits. Merit of fast convergence and demerit of the lack of guarantee of convergence. It might wander away, it might oscillate, it might diverge, such things may happen, and you can figure out that such things are most likely to happen when this matrix is close to singularity, because in that case the corrections will turn out to be so large up to which you cannot rely on a first order truncated Taylor series. So, what are the other methods? There is a modified Newton's method, and then there is a Broyden's second method. So, just like the second method of a single equation, for multiple equations also, for a system of equations also, you have a second method, in which this same Jacobian theme is used, but Jacobian is not evaluated at every iteration, because you see that it is costly, because for n functions you have to determine n derivatives. Okay, so, n square derivatives you need to evaluate, so that is costly. So, in Broyden's second method, the Jacobian is not evaluated at every iteration, but it is developed through some suitable updates at every iteration. Through the steps that we conduct, we get some idea about the derivative, and based on that idea we update, we keep on correcting the derivatives, we keep on updating the Jacobian matrix, and that way towards the later iterations we expect to find the Jacobian without actually evaluating derivatives. We try to develop a Jacobian which is close to accurate. The best formulation for nonlinear equation solving is through the method of optimization. You see that rather than asking for fx equal to 0, f1 0, f2 equal to 0, f3 equal to 0 and so on, if you pose the question as an optimization problem and you say we want to minimize this function, we know that the global minimum of this function is at that point where each of the squares is individually 0, right, because it is a sum of squares. So, this kind of an optimization based formulation for a nonlinear system of equations is typically the best among the nonlinear equation solving processes, and for this there can be, after you formulate it like this, in principle you can use any optimization method to minimize this function, but in practice we find that some methods perform better in this kind of a problem, some other methods do not do so well. Levenberg-Marquardt method is one optimization method which is particularly suitable for this kind of equation solving processes and least square minimization problems, which we will discuss later, because the proper appreciation of this method will be possible only after some discussion on the optimization methods of nonlinear optimization, a topic which we start from the next lecture. In the current lesson, these are the important points that we should keep in mind: the iteration schemes for solving single equations and Newton-Raphson method, which in most situations turns out to be adequate. If it is not adequate, then we look for certain other optimization based approaches, and other methods also have a connection with nonlinear optimization methods. So, next lecture we start our study of optimization methods, and along that we will see at the appropriate time what is the optimization based formulation for solving systems of nonlinear equations. Thank you.